Thank you very much. And now it's time for me to introduce our second speaker, or my second speaker, maybe your fifth or sixth speaker. Dr. Karen Wintersperger from Siemens. She's a research scientist and has a PhD in physics from LMU Munich while working on experimental quantum simulation. Her research interests include quantum computing for optimization problems, co-design of quantum computing hardware and software, as well as quantum simulation. That's also what her talk will be about. It's titled Investigation of Quantum Hardware Software Co-design for Optimization Problems. In her talk, she explores how hardware-software co-design approaches can offer a way towards practical utility of quantum computing. Dr. Wintersperger, the stage is yours. Happy to have you here at Quantum Summit.
Thank you very much. I think I can use this one, right? Oh yeah, perfect. So thank you very much for the kind introduction, and thank you for having me. I'm very happy to share some of our recent results on the quantum hardware software co-design for optimization problems. Okay, see, it's better to talk like this. So first of all, what do I mean by co-design here? So in general, it means to adapt the design of the quantum hardware and software to each other, but also to a specific application. And in our case, or in our experiments, it means that we considered NISQ devices for solving specific optimization problems. I think I need to move, yes. Okay. Okay, I do it like that, yeah. And the question that we ask here is, how should the hardware ideally look like to solve these optimization problems with a specific algorithm? So quantum hardware has many different properties that you can describe it with. Of course, the number of qubits, but also the qubit connectivity, the specific native gate set, or the noise level or gate fidelities, and many more. And in our experiments, we specifically considered the qubit connectivity. So as most of you know, I guess, if you do circuit programming, you usually don't care about the hardware in the first step, but you kind of assume all-to-all connectivity. But then when you want to run your program on a real quantum hardware device, you need to adapt it, so to compile the circuit to the properties of the hardware. And if your hardware does not have all-to-all connectivity, like in this sketch here, then usually what you do in a gate-based setting, at least, is that you introduce swap gates. And then it might be the case that you need to decompose those swap gates into the native gate set of the hardware again. So all in all, it means you get more gates, longer circuits, so also a longer runtime of the program, and a higher noise level if we're talking about NISQ devices, because each gate introduces, of course, a little bit of noise. So that means, of course, in general, we want not only to have large numbers of qubits, but also at the moment, we want to have very short circuits, ideally. In our experiments, we took the systems of IBM Q as a starting point for our investigations, and they have this so-called heavy hex topology, so that looks like this here. And what we did was increasing the connectivity or coupling density, as we call it, of these hardware devices. So then you can see on the right picture how that can look like. So we randomly added connections. And the coupling density that we use as a measure here is defined by the absolute number of connections in the hardware divided by the maximally possible number if each qubit would be connected to every other qubit. So all-to-all connectivity means a coupling density of 1, basically. And you can already see here how it looks like if you increase the coupling density from the original value of 0.014 to a value of about 0.1. And this is the main parameter that we changed in our experiments. We also had a native gate set, of course, that we used, and there we just took the native gate set of these IBM Q devices, and so far we didn't change anything here. And we also varied the backend size in some experiments, so basically the number of qubits then. And we considered different optimization problems, so namely the maximum cut or max cut problem, the maximum 3 satisfiability problem, traveling salesperson, and number partitioning. I think all of them are well known, and they all have also different types of applications, also in the industrial space, which I just mentioned there in the brackets, but I won't go into detail here. And we considered solving them with a quantum approximate optimization algorithm. I guess that's also known to mostly everybody, so I won't go into details of explanation here. I just added a little sketch. So we have several layers of gates that are parameterized, and you do a classical optimization loop to optimize these parameters to ideally prepare the ground state of your problem Hamiltonian. And the interesting thing here is for us, especially this part here that contains information about the problem Hamiltonian. So for example, in case of a max-cut graph problem, depending on the density of your graph, you also get different numbers of 2-qubit gates and so on. And this is what we are concerned with here. So what we did was taking this QAOA algorithm to solve these different types of problems with different problem sizes and so on, and then compiling these circuits to a specific hardware backend with varying properties such as varying coupling density, and looked mainly at the circuit depth or the number of swap gates, which is basically giving you a similar kind of information. And the first set of experiments that we published in that paper last year, that considered only the max cut problem. And the main result here is what you see when you plot the circuit depth versus the coupling density for different problem sizes also. So you can directly see that you get a strong decrease of the circuit depth, and first you get really this strong decrease, and then you see basically a saturation. So that means decreasing or increasing, your coupling density to, let's say, intermediate or relatively small values of 0.1, for example, already helps a lot in getting smaller or shorter circuits. And then going to all connectivity doesn't really change a lot anymore, so it basically saturates. So the main point we draw from this was that you not necessarily need all-to-all connectivity, but this kind of intermediate values might already be sufficient. And another thing that you can see is that with a higher coupling density, you also get a more favorable scaling of the circuit depth with the problem size. So it basically means plotting the data the other way around, now with this problem size, and then you can do a quadratic fit to these curves and plot the fit coefficients of this quadratic function, again with this coupling density. And the main part here is this quadratic contribution that again strongly decreases with the coupling density and then saturates. So that means also going to the slightly higher values already gives you a more favorable scaling in the sense of being, let's say, having a smaller quadratic contribution. And a second set of experiments, we then considered these 4 different optimization problems and basically compared the behavior of the circuit depth. So you can see here, I think very nicely, that for all of these different problems, so we have the maximum free satisfiability, the max cut, number partitioning, and TSP, and we see again circuit depth with the coupling density now in a logarithmic scale. But it basically looks all very similar, as you can, I think, obviously see here. So we get basically the same decrease and then saturation across all of these different types of problems. And I think that's already one important result when you really think of designing a hardware to an application. That definitely makes more sense if you can design a hardware, let's say, for a specific group of problems and not only just for a very special application. And motivated by this, we also found an underlying model for this decay. So it's basically an exponential model with 3 different parameters that gives you the circuit depth with this coupling density. You can fit that to all of these different curves, problem sizes, and problem classes. And then again, let's say as a quantitative measure of the similarity, we plotted the fit coefficients now with different problem classes being different colors. And you can nicely see that even like these coefficients quantitatively agree quite well for these different problem classes. So it really means we have a very similar decay here. So the reason, of course, for the circuit depth being decreased with coupling density is that you need less swap gates. And if you take a look here at the swap gate count, basically you also can see, first of all, that it's similar across the problem classes. And also you can fit the same exponential decay even in a simplified form. And we can again take a look here at these coefficients and see them basically lying on top of each other also for the different problem classes here. So that means, as I said, we have the exponential decrease, and also we get basically a saturation of the swap gate count starting at coupling densities of about 30%. And as another parameter that we looked at was the backend size, or number of qubits, and want to see if this basically changes this behavior. And so far we considered as a starting point this backend with 127 qubits, which are arranged in this pattern of 6 rows and 3 columns. And then we just extended that to larger qubit numbers by adding rows and columns. So we created backends with qubit numbers between 143 and 297 qubits. And the idea here is if you have a larger backend for a problem of the same size, that you might have, let's say, more possibilities to place your logical or your programmed circuit, so not logical in sense of error correction. You have more possibilities to place this circuit onto the physical qubit layout, for example. So if you have 2 qubits that very often talk to each other in your circuit, then you have the possibility to put them on physical qubits which are actually connected. And the idea was maybe if you have a larger backend, you have more possibilities to do this placement. But actually, at least for the problem sizes we considered here and these types of problems, it doesn't really make a difference. So we saw that this exponential decrease overall does not change, especially for the max 3 set and TSP. We really don't see a difference. So these are the green and the black curves here, like this. So they're even like also all the fit coefficients and so on really lie on top of each other. And if you're worried about the point clouds, these are basically the different backend sizes now here for, again, circuit depth and coupling density. We just set them off for visual clarity just that you get an idea of all the different points, but basically they lie on top of each other, which you can also see from the fitted lines. For the other 2 problems, like the max cat and number partitioning, you see slight variations in the asymptotes of the fit, like here for the very large coupling densities, but overall, like this kind of decay is not really changed by the backend size. That was just, let's say, an additional test that we did. So now to summarize, what do these results mean now if you think of designing a quantum hardware to an application? So first of all, as I said, we have found this underlying effective model. That means we have a similar decrease across different types of problems. And as I already said, I think that's kind of good news if you really think of designing a hardware to an application, because having a quantum hardware for just one very specific problem doesn't seem to be very scalable, let's say. So it's useful to say we design a hardware to a specific class of problems. And also, if we really think of, let's say, what connectivity do I need to solve these problems, we see that it might be sufficient to already have this intermediate coupling density of, let's say, 10%, because this already decreased the circuit depth quite a lot. So 10% in practice would mean that 1 qubit is approximately connected to 15 other qubits. So it's already much more than nearest neighbor connectivity, I have to say. And then we thought about how realistic would these changes be actually in practice on a quantum hardware. So since we started with these IBM Q devices, which are superconducting qubits, we also took a look there. So first of all, this relatively sparse heavy hex topology of IBM Q, I mean, that's chosen for a reason. Of course, I guess the IBM people here at the conference can tell you much more about that. But I think it's also meant to reduce crosstalk between the qubits. So this, of course, gets lower if you have a more sparse layout. But also, I mean, there exist other approaches like having nearest neighbor connectivity, for example, in the case of Google's quantum hardware. But there are also approaches to go beyond that with superconducting qubits. So for example, the ideas of coupling qubits to a quantum bus where you can then switch on and off the couplings and really only let those qubits talk to each other that you want to talk to each other. And or also thinking about 3D layouts, for example. There, of course, are also other platforms for quantum computers like ion traps, which already have all-to-all connectivity, but I think there are also other drawbacks, like I think so far the relatively low qubit numbers. There are also neutral atoms, where it's a bit easier to get at least these intermediate connectivities, but they're, of course, also still under development at a very young field, let's say. And another important approach is also, if you think of coupling density, to really have this shuttling, for example, with atoms or ions, that you can just bring together 2 qubits that you want to interact. So starting from these first results that we've seen here, of course, there are many other variables or parameters that you can investigate when thinking of designing quantum hardware. This is like the native gate set, or also studying effects of noise. You could also consider the actual integration of quantum computers with classical computers, for example, from a runtime perspective, or like how to connect those and what does it mean for timing overhead, for example. And also investigate the influence of the actual topology. So that means not only the number of connections, but also kind of the shape that the qubits are arranged in, at least in the case of superconducting qubits. So here, just some examples. You have the topology of Rigetti devices, the Google devices with the nearest neighbor connectivity, or also things like neutral atoms, for example. And with this, I'm at the end. I would like to thank our team from Siemens and OTH Regensburg, where we did this work in a collaboration. And thank you for your attention.
Thank you, Karen. So we have time left for questions if there are some.
2.5 minutes.
Don't be shy. Yeah, I can give you a microphone. It's better for the camera.
Thank you for the nice talk. So I have a bit of a technical question, which is with the calculation of the number of gates, did you just use the native compiler that comes with Qiskit, or did you experiment with different compilers, or have you thought about experimenting with different compilers to see if it also reduces?
Yes, we did. So we were also, first of all, on that experiment, we were using the Qiskit compiler. Sorry. Okay, no, I think it's changed by itself. And in the case of counting the number of swap gates, we basically just defined a new native gate set that contains the swap gates, so they are not decomposed, but just counted as gates. And then you can just measure the number. So that was using the Qiskit compiler. We also experimented with the TCAT compiler in the beginning, where we did, I think, for the MaxCAD problem, some first investigations, but we actually saw that the Qiskit compiler was performing better than TCAT in terms of circuit depth, which we didn't expect, but it turned out to be like that. So this is why we continued with Qiskit so far.
Does it answer your question? Perfect. So thank you very much. If there are more questions, I think you stay outside for maybe a little chat. Perfect. Thank you very much.